What is a logistic function? Why do we bother with them? Why are they in exam? Who knows? Well, there's some sketchy etymology behind the word logistic function. So basically we call it the logistic function because some French guy, Pierre-François Verhulst, was studying population dynamics and decided to name it such. There's actually a page on Wolfram dedicated to debating this topic with a semi-aggressive back and forth between UU and Max. UU eventually utilizes the nifty Google defined thing, but Google logistic, as in the organizational logistics, which comes from the French logistique, to house, which is valid. The function does relate to the holding capacity of the environment. Eventually, somebody looked this up on the French Wikipedia, which says basically the name logistic curve was given to it by Verhulst, but nobody knows exactly why. If you're feeling adventurous and your antivirus is up to date, you can go hunting for the original paper. I found it in a badly indexed file after about 15 minutes of forums and dead links, where he writes, "We will give the name logistique to the curve without any further explanation." So nobody really knows why it's called what it's called. So take that etymology. On the whole, though, the logistic function is a function that represents certain kinds of growth, kind of like the exponential function represents exponential growth, and linear functions can represent linear growth. Logistic functions are particularly nifty because they represent a particularly realistic kind of growth. So, to understand this, we're going to start off with talking about exponential growth. So with exponential growth, we start with a handful of triples, right? And those triples multiply according to an equation of the form x total equals xo times 1 plus r, all that quantity raised to the t power. But this equation has a lot of letters in it and is therefore tricky. We can plug numbers into this equation and get the triple growth equation, and using the data Spock provides for us. Hi Spock, that is one triple multiplying with an average load of 10, producing a new generation every 12 hours of the rate of 3 days. So using our equation, 1 times quantity 1 plus 10 raised to t, or 11t, where t is the number of generation triples measured in 12-hour increments. It's an exponential equation. It has a number of variables, so after one generation we have 11 triples. Equation tells us this, and this makes a ton of sense. One original triple plus 10 triple babies equals 11 total triples. There were originally 11 triples in this video, but I messed that up. After 24 hours we have t equals 2. We have 121 triples. This is 121. Then we have 11 third, 1,000 triples, 11 fourth, which is approximately 14,000 triples, 11 the fifth, 161,000, and then finally 11 sixth, which is exactly 1,771,561 triples, which is the exact number of triples Spock predicts. But the triple has a problem. The Enterprise has both limited food resources and limited space, and the equation doesn't account for this. So when the number of triples approaches infinity, when x approaches infinity with our previous equation, the equation is deviating from reality. Now, it's Chief Science Officer of Nerdist, Kyle Hill. The maximum population physically possible can be calculated from the size of the Enterprise. A lot of smart people evidently have spent too much time analyzing footage of the Enterprise making water landings and doing important physics things to calculate the volume of the Enterprise, all of which you can follow on Wired online publication. After using the laws of buoyancy and the like, we can actually determine that the Enterprise has a volume of 4.49 times 10 to the 5th meters third. So after about 100 hours of growth, there will be a little under 5 billion triples, enough triples to actually take up every last square inch in the Enterprise. So basically peak tripple. So would the tripple population look just like this? So we have our exponential, which is obviously not possible here, so we know the triple population can't look like this. So would it just be like this exponential growth with this weird cutoff thing? Not quite. Triple growth doesn't just stop all at once. For instance, triples in the control room without enough food and stop growing before triples in the hold. So there would be a point where only a fraction of the triples are multiplying, so growth would slow. So without hard numbers, we can predict that triple growth in a confined space would look like this. This is called a sigmoid curve because it looks like an S. What we can use to represent this function? Well, for the purposes of this exam and math in general, people came up with this great thing called the logistic equation, which is f of x equals L over 1 plus e to the negative k, x minus 6, 0, where e equals a natural Euler's number. XO is the x value of the sigmoid's midpoint, L is the curve's maximum value, and k equals the steepness of the curve. So let's apply this to triples. Immediately I write down the big equation, then I look at it and say, wait a minute, I don't have half of these variables. So I go back to the internet and do some more research, which we'll get to in a second. We'll need to infer some things here. For instance, depending on the variables, the curve could look like a couple of different things. So we need more given. So I go back to the original Star Trek footage and say, okay, what are some fairly accurate numbers? So when we look at the triples, one thing we're fairly certain of is that after 12 hours when t equals 1, there are exactly 11 triples. We're also fairly certain that before this, when t equals 0, growth is maximum. After this, not all the triples are guaranteed to survive. Some of them get that point gain, others wind up in like coffee and stuff. So to be honest, yeah, we're assuming little here, but it's good we get, so we'll accept this information as givens. As it turns out, AP and life in general doesn't care too much about this equation, they care about this differential thing over here. So going back, we have this differential, which is important. Most of the free response logistics on the BC exam give you this equation in this form. You need to remember what variable goes where, because they aren't going to tell you that on the AP, but they'll still ask about which variable means. And then we have here these related equations. There, and it's important to know, and we're still used for the problems we're making up an equation like these. Okay, but hold on those other equations. We're going to go back for a minute and look at the original equation. So where does this original equation actually come from? Well, fun fact, the equation I gave you in the first place actually comes from this equation. Yeah, this is the differential, is the kind of the original equation. It came first. So where does the differential actually come from then? Well, basically someone's saying I want the equation to have A, B, and C, and then adding variables until they got A, B, C. Other people on YouTube cover this, and you can look there, because we don't have a half hour. It's not covered in the exam, and I feel like I would mess it up pretty badly. Okay, pause for a minute. We're not actually attempting something that's useful, although all you future biologists and machine learning experts might need to know this later. However, to my knowledge, there isn't a problem this crazy on the exam. We're just using this sample to explore logistics and thinking about tribbles. Most of the AP problems revolve around that differential we saw earlier and are a tad easier. Alison will cover these later in the video, so if that's all you're here for, skip ahead. If not, and you want to know more about how these equations work, feel free to forge on. So basically, we're going to write down this equation to begin with. I'm just going to go over this generally, and you can zoom in and look at what I'm doing. So we write down the general equation, we fill out everything we know. We realize we don't know B. So if we actually look at equations that exist just because, we find that B equals P minus P0 over P0. So that's 5 billion minus 1 over 1 equals approximately 5 billion. So to solve for k, we need the data we inferred earlier from our original tribbles. We found that after 1 hour there'd be 11 tribbles, and so we plug 1 hour and 11 tribbles into the equation, and then we find that our only unknown is k. We go through, we isolate k, we raise things to powers, and then we take the ln of things. So we do all this crazy stuff. To check if this value is correct, we can plug in 3, and we can also take out our fancy graphing calculators and plug this in. So this wasn't going to work on your regular graphing calculator. Actually, I haven't tried. I'd guess if there'd be like some sort of Stack Overflow, but you can try this. Anyway, I use Desmos because Desmos is really cool. So we plug in this equation. We can check for like x equals 11. Everything checks out. We check out for 0. Everything checks out. If we zoom in way out, we do see that eventually when you get up to 5 billion, this equation does look like the logistic equation that we were going for. So that looks cool. If you hang on for a moment while I very bumpily zoom in, we see that this actually looks like we expect it to look like. So there's kind of this nice slowing down, even though from far away it looked like a right angle. Okay, so we checked that out and it looks cool. So we're gonna have Alison do some real examples, and then we're coming back to me for commentary. So Alison.
Let's start by reviewing the three forms of the equations. First, we have dp over dt equals kp times the quantity 1 minus p over L, or dp dt equals kp times the quantity L minus p. Then p equals L over 1 plus be to the negative kt, when b equals p minus p0 over p0. Therefore, there are three forms of the logistic equation, each useful in different problems. Two of these forms are logistic differentiable equations, which are derivatives. And the final, p, is one function. Let's do a practice problem. This is from the AP Exam BC 2004 question 5. A population is modeled by a function p that satisfies the logistic differential equation of dp over dt equals p over 5 times the quantity 1 minus p over 12. If p of 0 equals 3, what is the limit as t approaches infinity of p of t? If p of 0 equals 20, what is the limit as t approaches infinity of p of t? To answer this, we need to know for the logistic differential equation, the carrying capacity equals 12. By comparing this equation to the one we learned before, we can find that L is equal to 12. Therefore, we have found that the limit as t approaches infinity of p of x equals 12. For part B, we are asked if p of 0 equals 3, for what value of p is the population growing the fastest? Well, the population would be growing the fastest when p equals 1/2 of L. Half of 12 is 6, so the answer is 6. In part C, a different population is modeled by a function y, where dy dt equals y over 5 times the quantity 1 minus t over 12. We are asked to find y of t if y of 0 equals 3. The first step is separating variables. Therefore, we have 1 over y dy equals in the end the quantity 1/5 minus t over 60 dt. We integrate both sides and then exponentiate to get our final equation. Using our initial conditions, we find that k equals 3. Therefore, our final equation is as shown. Here's the second example. The rate in which the flu spreads throughout a community is modeled by the logistic differential equation of dp over dt equals 0.001p times the quantity 3000 minus p. If p of 0 equals 50, we're asked to solve for p as a function of t. So here we start with the formula we're given, and we'll compare it to a formula we have before. So 0.001 is k, and 3000 equals L. Therefore, the equation can be rewritten as such. Since b equals p minus p0 over p0, substituting in, we can find b equals 59. Finding all of our variables, we found that p equals 3000 over 1 plus 59 e to the negative 3t. Now to part B. In part B, we're asked to use our solution to A to find the size of the population when t equals 2 days. This is a rather easy substitution problem, where we substitute 2 in for t. So 2,607 people are sick after 2 days.
Okay, so to conclude, we're going to come back to the practicality of this equation. I mean, what people use it for. There's the obvious answer, of course, modeling population growth. That's actually what that Verhulst guy used logistics for back in 1838. Fun fact for all you AP human geos out there, Verhulst was inspired by Thomas Malthus's an essay on the principles of population. Other than that, surprisingly, this sort of thing is great for statistics and machine learning. It plays an important role in neural networks that Wikipedia goes over quite nicely. Chemists use it for reaction models, and this makes sense. Reaction proceeds exponentially, but is limited by limiting reactions. Particle physics uses it, and so does linguistics. In fact, economists and sociologists can apply it to the division of innovation. So, people do things with stuff they learn in this class, and logistics growth, that's really important too. Good luck on your BC exams, and when you see a logistic growth question, remember, it's no Tribble at all.